Okay, so today's lecture is about exercises on induction. Obviously, induction is not a very simple, it's not a simple proof techniques. And when you see this for the first time, I don't think you can get it right. So you need to see multiple times. And also, the homework problems are about exercise problem for the induction. Okay? And today's lecture could be important. As you notice, I usually write homework problems based on the lecture materials. So if you don't pay attention to the lectures, you may be having a hard time to do homeworks. If you understand what is going on in the lecture, it should be piece of cake, I hope. All right, so let me start with reviewing what is the induction. So mathematical induction, this is about to prove some sentences of the form P of n. So this is not a single sentence because n ranges over all possible values. Usually it ranges over natural numbers, but as you see sometimes it doesn't start with 1, it may start with 0, or it may start with 3 or 4 or whatever. Okay? So whatever the case is, there's a starting point, and then you do the induction using these base cases. So your goal is to prove P of n for all possible values. So let's say all possible natural numbers. And then a naive idea is trying to prove P of 1, P of 2, P of 3 separately. But you know this is not easy to do. Okay, but mathematical induction allows us to prove this in a different style. So first write this in terms of the base case and then some inductive case. Inductive case starts from assuming that P of m is true, then P of m plus 1 is true. So it is written in the style that when you prove each of these second, fourth, third, fourth, all these things, you assume that this is to be true, and then using this assumption, you prove P of the next number is true. Okay, so when you prove inductive step, do not worry about whether induction hypothesis is true or false. Okay, the reason is it is established before. So if we know that P of 1 is true as a separate base case, and if you know this is true, okay, even if at this point you didn't know that P of 1 is true, but if you combine the base case with the second formula, then you will derive P of 2 is true. And once you know that P of 2 is true, then using this one and the third formula, you can derive P of 3 is true, and so on and so forth. So you can derive all possible values of n, P of n is true. And the key idea here is if the same reasoning applies to these inductive cases, then we can write as a single step, abstracting away all the values of n. Okay? However, as we saw before, so basically what it means is to prove the case of P of m plus 1, you assume that P of m is true and try to prove P of m plus 1 using that assumption. And what is the assumption? Assumption is something that you didn't prove to be true, but you assume that to be true. And for this one, you can only use one induction hypothesis. So if you try to prove the case of P of m plus 1, you can only assume the case just preceding that m plus 1 case, which is m. So you can only assume that P of m is true when you prove the case of P of m plus 1. So if you want to prove P of 100, then the induction hypothesis should be about P of 99. Okay, so let me make that clear. So the problem, well, sometimes the induction fails. We saw some examples like fourth example of all Fibonacci numbers that even the caveat here is sometimes the reasoning is not repeated in all inductive cases. Some part of the steps, P of 1 implies P of 2, or maybe P of 2 implies P of 3, somewhere it may fail to use the same reasoning as in the other cases. Okay? So when you use induction to prove the whole other cases except for the base case, the assumption is this one. You have to check whether the same reasoning is applied to all inductive cases. Notably, in the horse example, not all the steps have the same reasoning. P of 1 implies so P of 2 couldn't have the same reasoning as the other cases, because when we have P of 1 implies P of 2, one condition that there are common forces between the two sets is violated. Okay? So that does not work. As well as in the Fibonacci number, which is actually shown in the next course of variance induction, some of these steps are actually not working as expected. So in the homework problem, I gave you some tricky questions. Well, not very tricky, but some alleged proof. They're trying to use induction, but it fails. Okay? So like the horse example. So when you solve those kind of problems, try to instantiate this argument. So like P of 1 implies P of 2, and so on and so forth, and see where in the proof this argument breaks. The same reasoning that usually applies to all other inductive cases may fail in some particular steps. The next one is causal values induction. And in this case, you are proving the step P of 1. So that's one case. The second case, P of 1 implies P of 2. The third one is P of 1 and P of 2 is true, then P of 3 is true. Okay? Now from the third line here is actually different from the mathematical induction, right? So we assume actually not only the previous preceding number can be assumed, but also all the preceding numbers, not just the one immediate preceding. So we assume that P of 1 and P of 2 are true. From this you derive P of 3. And same for the other P of 1 and P of 2 and P of 3. And then you try to prove it. The reason that we said here was the first case is actually the same as mathematical induction. If you know the first two formulas, you can derive P of 2. But since P of 2 is true and also P of 1 is true, their conjunction is true. If the conjunction is true and this third formula is true, then we can derive again P of 3. And P of 3 is true, P of 2 is true, P of 1 is true. So all their conjunction is true. With this formula as well as the last formula that is shown here, we can derive P of 4. So if you look at this, we prove P of 1, P of 2, P of 3, P of 4, forever. Okay? Now this way is a bit more complicated. It looks more complicated than the previous induction. But the nice thing about this proof is how many induction hypotheses that you have. So when you try to prove the case for P of m, you can assume that the induction holds for the value of n, value of 2, until value of n minus 1. So when you try to prove the case of P of m, you can assume n minus 1 induction hypothesis. When you have more hypotheses to play with, there is a better chance that you can prove. Now, the maybe a bit more challenging issue with the causal values induction compared to the mathematical induction is this. Not all the proof actually uses all assumptions. Okay, you don't have to use all assumptions. You can use some assumptions. Okay, P of m minus 1, same as in mathematical induction. Okay, so in that sense, mathematical induction is a special case of causal values induction. You can actually assume the two previous steps, so P of n minus 1 and P of n minus 2. And that was the case that we proved some property about Fibonacci number, because the definition of Fibonacci number is defined based on the two preceding numbers, right? So f of n is equal to f of n minus 1 plus f of n minus 2, when n is greater than or equal to 2. So in that case, it is actually good to use two induction hypotheses, which you couldn't do with mathematical induction, because mathematical induction, you can only use one induction hypothesis. So if you try to prove the case for P of n, you can only use P of n minus 1, but that is not enough for the Fibonacci number. Okay? So that's one thing. A bit thinking is required to use causal values induction. You can still use one induction hypothesis, but you can actually use not just the preceding one, you can use maybe 3 steps before. So if you try to prove P of m, causal values induction allows you to use the P of n minus 3. Okay? And that you will see very useful soon in the proof exercise today. Another thing is you have to check whether the same reasoning applies to all these inductive cases. Now, mathematical induction, also you have to check it, but for the causal variance induction, this is more serious. Okay, so you will see many times that some of the initial segment of the proof is not using the same reasoning. Okay, so you may have to separate these as different cases. Okay, so you're proving the same formula. Okay, so this formula P of n up to P of n minus 1 implies P of n. You're proving the same formula, but you may have to split the cases when you use causal variance induction. We'll see an example soon. Okay? And sometimes when these separate cases are not carefully checked, the induction fails. In fact, maybe the claim itself is false. Okay? So this was what I said before. To prove P of m, you can assume all the assumptions here, P of 1 through P of n minus 1, but you don't have to use that. Okay? You can use it, but you don't have to use it. Now, to prove this one, we actually used two induction hypotheses, which was this one and this one. Okay, any question up to this part? This is the review of the last lecture. Okay? So if not, then let's do more exercises. By the way, the TA should have gone through more induction exercise in the associated section. So that should be also something that you have to practice by yourself, whether you can prove these by yourself without looking at the solution. So why do we care about the induction in computer science? There are actually many uses of induction. I actually use induction heavily. My dissertation, I also use induction for some chapter. Unfortunately, teaching the use of induction in computer science to this level of class may be hard because you need additional knowledge about the structure of hardware and software and logic and formal language. But let me just mention some examples so maybe you can relate it later in the course. So one use is software and hardware verification. So when you learn like operating system, you want to see that whether the resources are fairly used. Okay, so whether there is no deadlock, so no process can continue to roll. How do we check that this system will not have deadlock? Okay, you can prove this by induction. You can think about the particular state of the system, and when you execute some instruction in a computer, that state changes to another state. And induction tells you that when you transition to another state, you will never reach into the deadlock state if your software design or hardware design is correct. Okay, so you can use induction for that kind of thing. And many times, this kind of induction involves about 1,000 cases to split because modern computers are very sophisticated. So we usually don't use our hand, but we can use some software to check this induction. There are some software, some theorem provers that check induction. Automated planning. So this is about an area of AI where you want to find a robot to execute some sequence of actions to reach a goal. When there is a goal, then the robot will find a plan. But how do you know that this goal cannot be reached no matter how many steps that you do? Okay, that can be proven by induction. Rule learning. This is inductive logic programming, where the idea is from the data is all raw numbers, so it's just some sensor data and any nonsensical numbers. But can you actually infer the meaning of the data? Can you extract the rules from the data? That uses induction. Formal language and number theory. Actually, if you go to 355, there are many of the inductive step of proof, like proof of pumping lemma, and many properties of formal language uses induction. Okay, and number theory, like Fibonacci number that we spoke about, a lot of numbers are defined recursively, and many of the recursive definition use the induction. Okay? So if you go to graduate school, you may even have a class, one course that is dedicated to induction. So in the whole semester, you're only learning induction. Okay, so we are not at that stage yet, but there's some non-trivial question that we want to consider. So here is a claim. So for all values n, so we are going to create a postage of n cent, where you can use only 3 cent stamps and 5 cent stamps. And from this, can we generate all possible stamps that is greater than or equal to 8 cent? So how can we do? So let's see, can we create like n equals 8? Okay, how do we create n cent postage or 8 cent postage using 3 cent and 5 cent stamps? Let me ask you, how can you create 8 cent postage? Okay, so how about you? 8 cent postage, how can you create 8 cent using 3 cent and 5 cent stamps? One of each, right? So one 3 cent stamp and one 5 cent stamp. So that is 8. So we can create 8 cent postage. That's good. What about n equals 9? How do we create 9 cent postage? 3 plus 3 plus 3. Okay. So that seems to be working. Okay. So 3 plus 3 is 9. What about 10? 5 plus 5. Okay. What about 11? 3 plus 3 plus 5. Okay. What about 12? 3 plus 3 plus 3 plus 3. Okay. So you see that it works for P of 8, P of 9, P of 10. So we prove, right? Right? Do you agree? Okay. It seems a good proof to you. So we proved it, right? So we show that for all possible values of n, we can create n cent postage because we show that this works. And if you write this way in your test or homework, you will get 0 point. Exactly 0 point. Okay, I promise you. I will never give any credit for the one who writes. This is a correct proof. Okay? So enumerating the cases is never a proof for this kind of argument. So you have to prove for all values of n that this should be true, but we only show 5 cases. But how many numbers are there that is greater than or equal to 8? It's very many, so we didn't do that. So we have to use induction. So let's use induction then. Okay. All right. So how do we prove? So proof is by course of values induction. So induction hypothesis tells us that for any k, so note here that the k actually starts from 8. So the induction is not starting from 1, okay, unlike the previous example, but we said this is okay. So induction hypothesis tells us that for any k such that k should be still greater than 8 because that's where the induction starts. But if k is less than m, okay, since this number k is less than m that we want to prove, by course of values induction that p of k should hold. Okay? So we say that for any k such that k is smaller than m, we assume by induction hypothesis that this is possible. Now the next step. Among the many values of k, so we want to prove whether we can create m cent postage. And by course of values induction, that allows us to assume p of n minus 1, p of n minus 2, p of n minus 3, and so on and so forth are true. Right? Which means in particular, when k equals m minus 3, Okay, by induction hypothesis, we know that there is a way to form the case-and postage. Okay, this is by induction hypothesis because k is less than m. So suppose somebody tells you I create a case-and postage, where k is m minus 3. Okay? Okay? So I give you the postage that is k minus k cent, which is n minus 3 cent postage. How can you create m cent postage using that? How do you create? So I just give you, I don't need to show you, but here is the n minus 3 cent postage. Okay, you can use 3 cent and 5 cent stamps. Can you create m cent postage? Add 1 3 cent stamps, right? Because somebody gave you m minus 3 cent postage, and you have to create m cent postage, then just add 1 3 cent stamp. So take that and add the 3 cent stamp, which will make the postage of m cents. Convincing? Yes.
How would you have made the assumption that K was the correct way to go, or that step B was the way to go for it?
I need to create a, let's say, postage of 15 cents. Suppose I have to do that. Okay? I want to create a postage of 15 cent postage. Now, somebody gives me 12 cent postage. Right? Then can I create 15 cent postage? I can do that by adding 1 3 cent stamps, right? And you're asking how do you create 12 cent postage?
I'm asking you how you came up with m minus 3 as like a good step.
Because that we have 3 cent postage, 3 cent stamps. So if somebody gives me n minus 3, I can always make n cent postage by adding 1 3 cent stamp. So that's why I chose y n minus 3. If I chose n minus 2, that doesn't work, right? N minus 4 doesn't work. But if I have n minus 3 cent, if I'm given n minus 3 cent postage, I just add 1 3 cent stamp, I can make. I could actually do this the other way. So I can create, so if somebody gives me n minus 5 cent postage, then I can add 1 5 cent stamp, then there's m cent postage. That's also another way to go. Okay? Yes?
So we could, for your induction hypothesis, we do k equals m minus the smallest unit of change. Or like, as in like.
I don't have to create smallness, but I could have used the other one.
Any units of change.
It doesn't matter. Okay. Very convincing, right? This is actually false. And I don't know, maybe this is actually wrong proof. Wrong proof. And probably don't have any idea yet. So let me actually show you a different claim, and we'll come back to this one. So this is the same problem as the previous one. The change here is instead of 8, I got this 6. So 6 cent or more cent postage can be created by using 2 cent and 4 cent stamps. Okay? So let's see how the proof goes. Okay? So proof by cause of values induction. Well, induction hypothesis tells me if I want to prove that I can create m cent postage, I can assume that I can create k cent postage where k is less than m, right? So same as before, right? And in particular, now I will take m minus 2. Okay, so let's take m minus 2. I know for some reason that somebody can give me m minus 2 cent postage. Then, actually by the induction hypothesis, we can create k cent postage. Okay, now take that and add 2 cent stamp. Then m minus 2 plus 2 equals m. So I created m cent postage. So according to the cause of values induction principle, the claim is proven. Convincing, right? Because there's nothing different from the previous one, except for some small number changes, right? Right? Okay. So can we create n-cent postage using 2 and 4 cent stamps. So let's see, 6. How do we create 6? Yeah, you can have 2 plus 4 or 2 plus 2 plus 2, you can do that. Okay, so that may be fine. So you can create n equals 6, 2 plus 4, okay? So 1 2-cent stamp and 1 4-cent stamp. How about n equals 7? What? That doesn't make any sense. You just prove it. Right? You just prove. How can it does not make any sense here? Why can you not make 7-cent stamps? So, right? You see, so it's strange. Yeah. What claim do you buy? Is it true or false? The claim is actually false. I think it's actually obvious, right? I don't have to go through all the inductive proof. With 7-cent stamp, how can you make using only 2 and 4? But if the numbers are much bigger than this, then you have to play with more cases, or it may not be as simple. It's just that for this problem, the numbers are so small, so we can easily say how many times that you apply many different stamps, you cannot get this case. So we know that this is false. Now, the claim was about for all values of n, but we found one single example so far that this claim is false. Okay? So this kind of example is called a counterexample. And to disprove the claim, you only need one counterexample. You don't need more than that. Because this is obviously false. But then the question is, what was going on in the proof? Okay? So it seems we are using the valid reasoning of induction, right? So what is induction saying? Okay, so let's go back. What was the causal values induction was to say, and you probably will get this hint when I show this again, right? So I told you to prove this. So P of 1. So when you prove the case of P of m, so if you are creating m-cent postage, you can assume all the preceding cases. So in the first example, with 5 and 3-cent stamps, we were using P of n minus 3. Assume that n minus 3-cent postage can be made, then we can create m-cent postage. So that seems to be fine, right? According to the induction principle, we were using P of n minus 3 as the induction hypothesis and proof P of m. What is wrong with that? And for the same thing, for the 2 and 4-cent stamps, we were using P of n minus 2 as the induction hypothesis. From there, we prove P of n. What's wrong with that? Maybe the textbook is wrong. Okay, so let me give you some time to think about, and let me actually give you maybe this problem. This problem is a bit easier than the previous problem, okay? Although syntactically they are almost identical. So let me open the Socrates and find out what is wrong here. You can talk with your neighbor if you want. Okay, let's see. Let me give you 30 seconds to close. And let's see.
Lines that are wrong or one?
Should be one.
That's just 1, 2 cents.
Choose the best one. So, all right, very close. Let's open the result. A few people didn't. Okay, let me try to close now. One more person has to finish. Okay, so let's look at the statistics. Okay, so according to the statistics, well, that's not majority, is more than half. So 20, 30%, 28%. So looks like C and E seems to be dominant as well as B and A. So it's not really demonstrative. Okay, let's see what is going on. Okay. So just compare the two proofs. And as you see, the proof is identical except for the numbers. So the numbers actually matter. Okay? Something that I ask you to do as a hint when we start, when we review the induction, was trying to instantiate this argument. Okay, don't take as just m or m minus 1 as granted. Try to write the instances of those m, and let's see how it goes. So this was the claim. The first thing, of course, you have to do is what is the mathematical sentence that you want to prove. So you have to identify what is P of m. Okay, in the homework, I usually ask you to state clearly what is P of m that you want to prove. Okay, so for this problem, P of m is a sentence that can be either true or false. And the sentence is saying it's possible to produce m cent of postage using 2 cent and 4 cent stamps. Okay? This P of m, okay, is a declarative sentence. Okay? That can be either true or false. Okay? Although it's actually false. Okay? Now, if we are trying to use course of values induction, what are we showing? We are showing this form, P of 6, because induction starts from 6, when n equals 6. Okay, so if you are trying to prove the case for P of m, assume that all the preceding cases can be done. So when you try to create n cent postage by course of values induction, you can assume that n minus 1 cent postage can be created, n minus 2 cent postage can be created, up to 6 cent postage can be created. These are the assumptions that you can use. Okay? So let's try to instantiate this. So by instantiation, I'm checking this with respect to each possible values of n. Okay? Because I told you before that even if this is one line, maybe for some values of m, we may use different reasoning. And in that case, you cannot claim as one inductive step. So let's see, m equals 6. P of 6. Is it true? So we have to prove P of 6, right? Because when you try to prove P of 6, this is empty, right? So there is no preceding numbers that is less than 6 and starting from 6. There is no such cases. So there is no induction hypothesis that we can use. So you have to prove P of 6 directly. Is P of 6 true? Yes. How do we know? We can just show it. We can use 2 cent and 4 cent stamps, so we can do that. M equals 7. Now, if you look at m equals 7, there's an interesting thing going on. The statement here is instantiated to be this way. How many induction hypotheses do you have? One. This is induction hypothesis. This is the conclusion that you want to draw. And for this time, you can use induction hypothesis for P of 6, which means in English, it is possible to produce 6-cent stamps using 2-cent and 4-cent stamps. From this, can you create 7-cent postage? Knowing that you can create 6-cent postage, does that help you to show that 7-cent postage can be made? Does not work. Somebody asked the question, why n minus 3? Because we have 3-cent stamps. We don't have 1-cent stamps, so even if you can make, even if P of 6 is true, even if this is true, okay, you cannot add 2-cent stamp to create 7-cent postage, right? Even if somebody gives you 6-cent postage, adding 2 or 4-cent stamps there doesn't make 7-cent postage. This is false. The reasoning here, okay? So going back to the previous sentence, what was going on here? Okay, let's look at this one. So we are looking at m equals 7 case. Suppose m equals 7, okay? The part B, you're saying that k equals 5, right? If m equals 7 that you want to prove, then k is 5. And line C is saying, by the induction hypothesis, there is a way to form 5-cent postage. However, induction hypothesis is starting from 6, when n equals 6. It doesn't cover n equals 5. We do not get P of 5. Let's go back. If we want to apply the same reasoning, what could have been helpful is not P of 6. We need induction hypothesis to be P of 5. If you can create 5-cent postage, then you can create 7-cent postage. But according to the course of variance induction that starts with n equals 6, we cannot assume P of 5. P of 5 is not upon your hand. In fact, this is the case that the reasoning fails. Okay? Even if you can create 6-cent postage, which happens to be true in this problem, it does not help you to create 7-cent postage. The reasoning that you create a minus 2-cent postage and then add 2-cent stamp, that does not hold for this step. Are you together? This is a bit tricky, okay, but hopefully you can understand, because one of the former problem is about the postage problem. Okay. So this is the failing case. What about the other cases? So when n equals 8, that means you have m equals 8. So this means P of 6 and P of 7. So we have two induction hypotheses. Among them, I'm going to use only P of 6. Okay? So P of 6 means assume 6-cent postage can be made. And can we create 8-cent postage? Yes, just add 1, 2-cent stamp. What about m equals 9? In this case, I will rely on this one. Okay? So we assume that 7-cent postage can be made, and we can create 9-cent postage. Done. And this reasoning go on forever. Except for the case when m equals 7, where we couldn't use P of 5 as induction hypothesis because induction starts from 6. So the answer to previous question is C. C is false. You cannot create case and postage. Okay? That's not by induction hypothesis when m equals 7. All right, so okay. Any question? Yes.
So, even though in line B, that's when you're subtracting 2 from K to be less than 6, it's still incorrect in C.
Yeah, that's just a equation number, right? It's arithmetic. So you can take off 3 or 2 from the number. That does not make any difference. The wrong claim, going back to this one, the wrong, so, I mean, here K equals 5 is fine, but this is the problem. The C, okay, doesn't say that you can create a postage of 5 cents. Induction hypothesis does not cover the case when K equals 5 because it starts from 6. Okay, so going back to this thing. Okay, so induction hypothesis starting from 6 doesn't have P of 5. Okay, so all right, let's look at this one. So when m equals 6, we can create it. When m equals 7, we know that P7 is false because there's no way to form it. While in case 3, when m is greater than or equal to 8, the inductive step itself is fine. Because if you assume that P of m minus 2 is true, note here that m here starts from 8. In that case, k starts from m minus 2. Right? So which means k starts from 6. So when m equals 8, k is 6, which is covered by the induction hypothesis. Okay? So you can create, say, 6 cent postage, and you can add 1 2 cent stamp to make 8 cent stamp. That is fine, starting from 8. If m equals 9, you can create 7 cent postage, and induction hypothesis covers that, so you're fine. When m equals 10, okay, assume P of 8 is true. That is also covered because that's in the induction hypothesis. You can assume it and add 2 cent stamp. So this one plus 2 is 10. We are done. Okay? The only problem is here. When 7 cent postage, when you create 7 cent postage, you cannot assume that 5 cent postage can be made because that's not covered by the induction hypothesis. Okay? So then, what was going on with this guy? So, same as before, proving this for when m equals greater than or equal to 8, okay, is proving this case. So assume, starting from P of 8, P of 9, up to P of m minus 1. Let's assume that these are all true. Then we can create m cent postage. Again, try to instantiate this. When m equals 8, so when m equals 8 here, m equals 8 here, right? This is empty, right? So you have to prove P of 8 directly. When m equals 9, okay, 8, so this induction hypothesis goes from 8 to m minus 1. So m minus 1 is 8. So you can use one induction hypothesis when m equals 9. When m equals 10, you can assume starting from 8 up to 1 less than 10. So you can assume these two induction hypotheses. When m equals 11, you can use P of 8, 9, 10 can be created. When m equals 12, you can assume that 8 cent or 9 cent or 10 cent or 11 cent stamps can be made. Good. So again, what is wrong with this proof? The proof that we saw. So if we create, say, 9-cent postage, according to that claim, what was assumed to be true? P of 6, right? So 6-cent postage can be made, then we can add 1 3-cent stamp, so we can make 9. But the induction doesn't tell you that you can use P of 6 because it's not part of induction hypothesis. Same way, if you want to prove P of 10, okay, m minus 3 is 7. But induction doesn't tell you that P of 7 is true. It could be true, but induction itself does not say that P of 7 is true. What about this case, P of 11? P of 11, m minus 3 is 8. Oh, this is fine. From this on, there's no problem, because once m equals 11, I can assume that m minus 3 cent postage can be made. That's one of the induction hypotheses. When m equals 12, I can say P of 9 is true, so that's fine, and so on and so forth. We are happy, starting from m equals 11. The only problem is when m equals 10, 9, 8, induction hypotheses do not help us. Yes.
Would you be able to just manually do
Yes.
the mechanical
So that's a separate case that we have to prove. Okay? So induction doesn't mean that it is false. There may be another way to prove it. Okay? So here is the correct proof. I told you we are still proving the same formula as you see here, but for each of sometimes you have to split the cases. Okay, because sometimes induction does not cover. So P of 8, to find 8-cent postage can be made, we cannot use induction hypothesis. It could have been P of 5, but P of 5 is not in the induction hypothesis. Okay, so we have to show manually. How do we find 8-cent postage? Well, 3 plus 5 is 8. That's what we did in the beginning, if you recall. M equals 9, we actually did that. 3 plus 3 plus 3 is 9. M equals 10, 5 plus 5 equals 10. Until now, we had to separate these cases out. But now, with case 4, when m is greater than or equal to 11, now we can safely use induction hypothesis. Because when m equals 11, then 11 minus 3 is 8, and 8 is allowed to be assumed by induction hypothesis. Okay, this whole thing starts from n equals 8. Okay, so case 4, when m is at least 11, then by induction hypothesis, P of n minus 3 is true, because n minus 3 is greater than or equal to 8. Okay, so it is possible to form a postage of m minus 3 cent by induction hypothesis. So you can add 1 3-cent stamp, that makes m minus 3 plus 3 is m cent postage. So P of n is found. Okay? So you can easily play with all these numbers. For some numbers, you can create any cent of postage. For some other pairs of stamps, you cannot create any cent postage of any cent. Okay? So try to compare between these two proofs. They look very similar. Okay? The alleged proof that I showed before. Okay? But the first claim, okay, using 3-cent and 5-cent stamp, the claim is actually true, happen to be true. With slight modification, the second problem, 2 and 4-cent stamp, the claim is actually false. But if you're not careful in using this induction, you may end up with proving anything is true. Okay, like fourth example. Okay, so question up to this part before we move on to different topic now. Okay, if not, then let's look at the last topic of today's course. So we are going to apply causal values induction for propositional formulas. And recall that we have studied the syntax. Okay, so maybe this is a good time that you browse all the materials that you learned in the beginning. So every atom is a formula, okay? And bottom and top are formulas. And if F is a formula, then this string left and negation F closing parenthesis is a formula. Okay? Or if you have any binary connectives like conjunction, disjunction, implication, okay? If you have a G formula, then this string is also a formula. This was one of the slides that you saw earlier. I think it was lecture 2 probably. Okay. So that was the definition, and the definition is so-called recursive because to define a formula, we refer to a formula again, right? Now, for this kind of recursive definition, I told you that induction is a good way to prove the property. Okay? So we want to prove some properties for any formula. So one of the maybe trivial property of formula is when you take any propositional formula, you will see that there is an equal number of left and right parentheses. Right? You can play with some examples like what? How many left parentheses are here? 1. How many right parentheses? 1. So that's equal, right? If you have, how many left parentheses are here? 3. How many right? 3. So no matter what you form, you see that there are same number of left and right parentheses. So the claim that we want to prove is this. P of F, so now this induction is not about the numbers, it's about the structure of the formula. Okay? P of F means that the formula F has the equal number of left and right parentheses. How can you prove it? Again, enumeration does not help, right? Because how many formulas are there in the world? Infinitely many. You can create many, many different formulas. And you cannot check for each of case that they have same number of left and right parentheses. So that's not possible. Okay. So we are going to prove this by causal values induction. And for the formulas, there is a template for the causal values induction. So this template is saying, based on the recursive definition, to prove that it is property P or for any formula F, you need to establish these 4 cases. First case, when F is an atom, F has that property P. This is kind of base case. You can check it without using induction hypothesis. Case 2, again, it is similar to the first one. So there are 2 zero-place connected, top and bottom. So in that case, those has the same property P. From the third and fourth bullets are for the inductive cases. So here, if a formula has property P, okay, then the new formula that can be defined by the third recursive clause, that formula also have the same property P. First one same. Okay. If F and G have property P, then so you assume this as an inductive step, inductive hypothesis. Using that, you show that the new formula, F sum G, also have the same property P. If you show all 4 cases, then you're done with covering all possible formulas because any formula can be made using these rules only. So I have 2 class discussion problems for the next time. Which is to use this causal values induction. So if you want to volunteer for the problems, then you're welcome to do so, as well as there's a homework problem that uses causal values induction. So let's look at this problem to give you some idea about how to use the induction. Okay? So the claim is If you take any propositional formula, there's always equal number of left and right parentheses. Maybe this is too obvious, but it's not that obvious to prove. Okay? So, before we prove this, I'm going to introduce the notations. I'm going to say L of f. I use square bracket just to differentiate between the parentheses in the formula. So this is number of left parentheses in the formula f. And same way, I will denote by R of f the number of right parentheses in f. Okay? Okay, so recall the proof cases. So case 1 is when f is an atom. Okay, so atom is like P, Q, R, right? Okay, so in this case, what is L of f? When f is an atom, how many left parentheses are in there? How many left parentheses are in atom? 0, okay. So there is no parenthesis in atom. So L of f equals 0. What about R of f? How many right parentheses are in the atom? Also 0. Oh, by the way, I should actually say what is the claim that we want to prove. The claim here, as in English, can be written as proving P of f, where L of f is equal to R of f. So this is the claim to be proven. Okay? So what did I just show you? Well, if f is an atom, these two are equal, so that's what we wanted to prove. Okay? When f is an atom. Case 2, when f is zero place connective, bottom and top, I also want to show the same thing. Okay? And how many left parentheses are in bottom or top? Also 0. So it's actually the same reasoning as before. Okay, so these are the base cases. And that's easy because there are no parentheses in those two cases. What about case 3? So case 3 is saying that if f has the property P, assuming that f has the property P, that's an induction hypothesis, prove that parenthesis, negation f, closing parenthesis, have the same property P. Okay? So, induction hypothesis is saying that assume L of f is equal to R of f for formula f. Okay, so this is induction hypothesis. Okay? Now what we want to prove, the goal, let me just copy the goal here, it's not yet proven, but what we want to show is this new formula that precedes the negation, it also have the same number of left and right parentheses. So this is the goal that we want to prove. Okay, note here that this is P of f, and this is P of not f. Okay, so we assume that the property holds for f, and then using that to prove that not f also has the same property. Okay, so this goal is not yet proven. So how do we prove it? So here is something that we can use induction hypothesis. How many left parentheses are in L of this formula? How many parentheses are here? How many parentheses are there? I don't know because I don't know what is F, right? However, I can actually say that the number of left parentheses in F is denoted by L of F, right? So then I can write this as an equation. Okay? So the number of left parentheses here is this one, right? Plus whatever is in F, whatever left parenthesis in F. So this number is 1 plus, 1 denotes the first left parenthesis in here, plus L of F. You should understand this, otherwise you cannot follow the rest of the steps. How many of you don't understand the equation that I just wrote? So all of you understand? Okay? Yes? You don't? Okay, good. Suppose F is an atom, P. How many left parentheses are here? 1. 1 plus 0. Right? Suppose this F has 1 left parenthesis. Then how many left parentheses are here? 2. Because 1 plus 1. If this has n number of left parentheses, then how many left parentheses are in the whole string? 1 plus n. Yes. So you know that now. Good. Okay. So that's what I denote by 1 plus n. So where n is the number of left parentheses in F. Good. Okay. Now I claim that this is same as 1 plus R of F. Why? Why 1 plus L of F is equal to 1 plus R of F?
They'll be the same amount.
How do you know that they are same?
Because if there's a left parentheses, there's going to be a right one.
We know V is true.
Let's be simple. There's a solution already in the slide.
It's from our assumption that LF.
Yeah, we already wrote the assumption here. L of F is equal to R of F. Okay? And as well as with other induction hypotheses, do not worry about whether this is true or false. This is given to you. And this one is simply add 1 to each side. Okay? In algebra, if you add the same number to both sides, then the resulting equation is still true. Right? But why do I write this? It's because this number is same as number of right parentheses in here. Okay? Why? The same reasoning applies. The number of right parentheses in the whole string, parentheses, negation, F, closing parentheses. How many right parentheses are here? This is not. But F may contain, say, n right parentheses, followed by another one. So 1 plus n, where n is the number of right parentheses in F. So this equality is true by definition. And this equality is true because this is induction hypothesis. Again, this is the definition of left parentheses. So what did we prove? If we look at the chain, we prove that this one is equal to this one, which is similar, which is actually the same thing that we wanted to prove. So this P, the property P, also holds for negation of F. So case 3 is done. Let me actually recap what we are doing. So we are using this one. If a formula F has the property P, if F has the same number of left and right parentheses, then not F also has the same number of left and right parentheses. That's what we just showed. So they have the equal number of left and right parentheses. There are equal number of left and right parentheses in F, and that means L of this new formula, which has 1 plus whatever the number of left parentheses in F, is equal to 1 plus R of F, because L of F is equal to R of F by induction hypothesis. And this number is the number of right parentheses in this new formula. So we are done. Okay, case 4. In case 4, if you recall the previous one, we assume this induction hypothesis for two formulas. So we are going to say L of F is equal to R of F. And L of G is equal to R of G for formulas F and G. So we are assuming the induction hypothesis for the subformulas F and G. Now, let's see, what we want to prove is the new formula that uses this binary connective, I use just sun to denote any kind of binary connective, should be equal to the number of right parentheses in the new string. I have to show this, right? So we have to fill this gap, okay? So how many left parentheses are in this formula? Can anyone tell me how many are there? Huh? Use the thing that you know, like the previous case. 1 plus the number of left parentheses in F plus number of left parentheses in G. So using the notation, we can say that this is L of F, 1 plus L of F plus L of G, right? I don't have to know what is the exact number, I don't need to know, because L of F encapsulates all the number of left parentheses in F. So this is the first left parenthesis, and whatever the number, let's say M, plus whatever the number N, that's what I write here. Okay, now you know the trick. L of F is equal to R of F. So I can change this to, instead of L of F, I can write R of F. And I also know that L of F, G equals R of G, so I can write R of G. Right? But then if you look at this number, this is exactly the number of right parentheses in here. Okay? So L of F plus L of G plus the last one. That's the total number of right parentheses in F sun G. So we proved that all these four cases, okay, is true. So by the force of values induction principle, this property is true for all formulas. All right. So I want you to actually go back to this one. The next problems are similar, but maybe a bit more complex, but the same idea applies. So the next time, if you have solution for these problems, you can write your solution on the board. Here is a notation for the prefix. So when you say a prefix, you have like for this kind of formulas, right? So prefix here simply means that any prefix of the string. Okay, the mathematical definition is, and you have the string a1 .an, where each AI represents an alphabet symbol. We are taking any smaller initial characters. Okay, so if you have this as your string, how many prefixes are there? The first one is actually empty string, is a prefix. Okay? And this is also a prefix, taking only one. Or taking 2 is also a prefix. Taking 3 is also a prefix. Taking 4, also a prefix. Taking whole is also a prefix. So this formula has 1, 2, 3, 4, 5, 6 prefixes. So you get it, right? So prefix is just initial segment. Okay, any initial segment. Now D5 and D6 is about the properties of the prefix. So if you take any prefix of a formula, for this one, the number of left parentheses is always greater than or equal to the number of right parentheses. Right? We can easily check for this example. L of F is 0, R of F is 0. L of F equals 1, R of F is 0. So there are more left parentheses. There are more left parentheses, more, equal. So at least for all the prefixes, the number of left parentheses is at least greater than or equal to the number of right parentheses. How do you prove it? All right. The other one is any prefix or formula is either an empty string or has more left than right, or equals F. So for example, these are the all characteristics of that formula. So the first one is empty string. The second one, this one, they all have the more number of left parentheses, while the last one has equal number of left and right parentheses, and it's actually exactly the same as the given formula F. Okay? So whatever prefix that you take, you will always see one of these three cases will apply. That's what P6 is about. Okay, any question about today's material? This is the last one. If not, then let me open this operative.